Hello, welcome. In this short video, I will derive the probability distribution of the estimate of a variance given two observations. That is, given two observations that have a normal distribution with mean equal to 0 and variance equal to sigma square. It is two observations x0 and x1 that have a normal distribution with mean equal to 0 and variance equal to sigma square. So given this information, I want to derive the PDF of the PDF or the probability distribution of the variance estimate given by sigma square hat is equal to 1 by 2 x square of 0 x of 0 square plus x of 1 squared. So we want to derive the probability distribution of this variance estimate given these two observations. So in order to derive the probability distribution of sigma square hat, that is the variance estimate, first we need to know the probability distributions of these individual components. We need to know the distribution of x of 0 squared and also the distribution of x of 1 squared. So first we will determine the probability distribution of x square of 0. That is, let a random variable y0 is equal to x square of 0. The probability distribution can be determined as follows. That is, the CDF f of y0 is equal to probability that the random variable y0 is less than a value y0, a small case y0, and which is equal to probability that x square of 0 is less than y0, since y0 is equal to x square of 0, and this is equal to probability that x of 0 is less than square root of y0. And since we know the probability distribution of x of 0, we can determine the PDF or probability density function of y0 at y0. So f of y0 at y0, that is the PDF, is equal to the derivative with respect to y0 of the CDF. And this probability can also be written as the CDF in terms of x0 at square root of y0. So this is equal to the derivative with respect to y0 of the function, the CDF f of x fx0 at square root of y0, which is equal to, first we need to find the derivative of the square root of y0, which is 1 by 2 times square root of y0, and then the derivative of the CDF function, which is the PDF function, that is defined as fx0 of square root of y0. And this PDF f x0 is, from the given information, a normal distribution with mean 0 and variance sigma square. So by using that information, we have 1 by 2 times square root of y0 multiplied by square root of 2 pi into sigma square multiplied by exponential of minus square root of y0 whole square divided by 2 times sigma square. Upon simplification, this is equal to 1 by 2 times square root of 2 pi sigma square y0 multiplied by exponential of minus y0 by 2 sigma squared. Therefore, the probability density function of y0 at y0. The probability density function of y0. Along same lines, we can also determine the probability density of y1, where y1 is equal to x square of 1. Therefore, the probability density of y1 is equal to 1 by 2 times square root of 2 pi sigma square y1 multiplied by exponential of minus y1 by 2 sigma square. So these equations give the probability density functions of the squares of the observations. Now we want to find the probability distribution of sigma square hat, which is defined as the sum x square of 0 plus x square of 1 over 2. And this is equal to, from the assumptions that we have, from the definitions we have, that is y0 is equal to x square of 0 and y1 equal to x square of 1. This is equal to 1 by 2 multiplied by y0 plus y1. And we already know the PDFs of y0 and y1. And since x of 0 and x of 1, that is the two observations, are independent of each other, we can safely assume that their squares, that is y0 and y1, are also independent of each other. So let z equal to z1 by 2, where z1 is equal to y0 plus y1. And since y0 and y1 are independent of each other, and we know their probability density functions, we can easily determine the probability distribution or probability density function of z1. The probability density function of z1 is defined by the convolution of probability density functions of y0 and probability density of y1. The proof for this theorem is given in a previous video. So equation 3. So by using this definition, the probability density, that is basically for two random variables that are independent of each other, the probability density function of their sum, that is z1 equal to y0 plus y1, is given by the convolution of the probability density functions of the individual random variables. So by using this theorem, we can determine the probability density of z1 as integral 0 to infinity. Since y0 is equal to square of x of 0, its limits are 0 to infinity. So the probability density function is integral 0 to infinity multiplied by fy0 of y0 multiplied by fy1 of z1 minus y0 over y0. That is, integration is over y0. So this is the definition of convolution function. So by using the results from equations 1 and 2, in the definition of the probability density function of z1, that is over in equation 4, we have fz1 of z1 is equal to integral 0 to infinity 1 by 2 times square root of 2 pi sigma square y0 multiplied by exponential of minus y0 by 2 sigma squared. And for this function, that is fy1 of z1 minus y0, we have 1 by 2 times square root of 2 pi sigma square z1 minus y0 multiplied by exponential of minus z1 minus y0 divided by 2 sigma square. And the integration is over y0. So upon simplification, this integration becomes integral 0 to infinity 1 by square root of y0 multiplied by z1 minus y0 dy0. And the rest of the terms are 1 by 2 into 2 is 4, and square root of 2 into square root of 2 is again 2, and we have pi. So this is 4 into 8 pi sigma squared multiplied by exponential of minus y0 by sigma square minus z1 minus y0, that is z1 minus y0 divided by sigma square. Therefore, the probability density function of z1 is 1 by 8 pi sigma square multiplied by exponential of minus z1 by 2 sigma square. Of course, there is a 2 sigma square over here and here. And then there is an integral 0 to infinity 1 by square root of y0 into z1 minus y0 dy0. Now by using a parameter transformation defined as y0 is equal to z1 into u, we can easily see that this integral becomes a function which is independent of z1 as follows. That is, this is equal to integral 0 to infinity. That is, even when you use y0 equal to z1 into u, the limits won't change because they are from 0 to infinity. So they are 0 and infinity. So this becomes 1 by square root of z1 into u multiplied by z1 into 1 minus u multiplied by z1 into du. So clearly the value z1 cancels and we are left with integral 0 to infinity 1 by u square root of 1 by square root of u into 1 minus u du. So let us call this the function which is independent of z1 denoted by letter a. So the probability density function f of z1 is equal to a upon 8 pi sigma square exponential of minus z1 by 2 sigma square. And since z is equal to z1 upon 2, that means we can easily replace z1 with 2 times z. Therefore, the probability density function of z, that is the estimate of variance, is given by a upon 8 pi sigma square exponential of minus sigma square hat divided by sigma square. Therefore, the probability density function of the estimate of variance is an exponential distribution. Here note that z is equal to sigma square hat is equal to z1 by 2. Thanks for watching.